All right. Now that we've talked about electric flux, we're going to go through one of the main results relating to electric flux, known as Gauss's law for electric fields. So, we'll eventually do some pretty involved derivations with Gauss's law, but today we're just going to introduce it. So, to begin, we're going to review our statement of Gauss's law as it applied to magnetic fields. So, remember that since every magnet has a north pole and a south pole, this means that there can't actually be any net flow into or out of a 3D surface for magnetism, at least, because any field line that entered also exited, and vice versa. And this was because you can't have magnetic charge by itself. For every north, there was a south. But of course, we know that point charges are very real things that exist for electric fields. And based on the source and sink rule, if I have a bunch of positive charges together, there should be a flow out of that area. And if I have a bunch of negative charges together, there should be a flow into that area. So Gauss's law for electric fields states not that the flux is zero, but that the flux depends on the enclosed charge. And it's interesting that the surface you use is actually irrelevant, and it actually only depends on the enclosed charge. And we verified this in the spherical case and kind of reasoned through it that the flux actually doesn't depend on the surface, it's only the enclosed charge, because areas increase quadratically with distance and fields shrink quadratically with distance because of the inverse square law. And those two effects of E sort of being quadratic and area being quadratic but in a different way, we see that it actually results in a constant flux for whatever surface you draw. And we'll take advantage of that in our next section. So these are two of the four main results of E&M, known as the Maxwell equations. So the magnetic field form of Gauss's law basically states magnetic monopoles don't exist. There's always a north and a south paired. But the electric field case states that positive charges are sources of electric field and negative charges are sinks for electric. So first, we're going to just compare each of these forms of Gauss's law and just kind of reason that this makes sense. So first, we're going to draw any surface enclosing the bar magnet, and we want to verify that Gauss's law for magnetic fields is satisfied. So again, we have to do this with closed surfaces. So this is just something with an inside and an outside. I'm going to keep it simple and draw maybe this shape. So you can think of this as a cross section of a surface you'd like. So I'm essentially shoving this bar magnet into a football. And we want to verify that there is no net flux through this surface. So let's say I have a field line that sort of exits right here, comes back around, and goes through there. I'm really bad at drawing magnetic lines, so maybe I need to guide myself a little bit. So roughly, I'm going to draw a field line maybe like this, and I'll draw a field line like this. Okay, slightly better. But we see that regardless, using our sources and sink rule for magnetic fields, we see that all the field lines that entered the surface also exited. So we see that magnetic flux was equal to zero. All lines that exit the surface also enter. Because we don't have any sort of net flux because all the lines that exited also came back in. So there is no net sort of source or sink happening with this. But then if we draw an enclosing surface for my point charge, we don't get the same thing at all because a point charge, well, that's a source. That's a source of field lines. I can line it up better. That's a source of field lines. So we get something that looks like this. our field lines are going to point radially out of this point charge. And of course, they're never going to come back. So for Gauss's law with electric fields, our electric flux is positive, because this means that positive charges are sources of field lines. So again, Gauss's law, if we just kind of compare why these are different, well, it's because electric fields and magnetic fields have these different properties. But why does Gauss's law take this different form? Well, it's because magnetic monopoles do not exist. And instead of monopoles, we might want to call it a point charge. Magnetic point charges do not exist. There's always a north and south paired together. And that's very different than the electric field case where you just have these isolated charges. So I've shown some cross sections of surfaces here. So I have all these charges that exist in space. So you could consider maybe these are like spheres, like a sphere here, a sphere here, a sphere here, and then there's a big enclosing ellipsoid. And we just want to rank the net electric flux through each of these surfaces from most negative to most positive. And I didn't have to give you any parameters about these surfaces because we know from Gauss's law, and we'll probably zoom back in. We know from Gauss's law that the net flux through a surface is equal to Q enclosed divided by epsilon naught. So what that means is that when we're doing our ranking here, we know that the flux is proportional to Q enclosed. So we can actually just figure out what each of the Q enclosed values are for our four surfaces. So let's look. So for A is pretty simple. It is just enclosing a point charge of plus 2Q. So Q enclosed is equal to plus 2Q. So it's going to have positive flow out of the surface. Case B, well, that's a negative charge. The negative 2Q enclosed, that's going to be a negative flux flow into the surface. C encloses a 3Q. It's also going to be flow out of the surface. And then D encloses everybody. So we actually have to do some math here, but we can see that in case D, it encloses A, B, and C, the charges inside those surfaces. And A and B have the same charge but opposite sign, so those actually cancel. So for D, the enclosed charge is plus 2Q minus 2Q plus 3Q, which is equal to plus 3Q. So we have 2, negative 2, 3, and 3 as our enclosed charges, and we just rank them from most negative to most positive. So our only surface with negative flux is B. Then A has some positive flux, and then C and D actually tie for the most positive flux. And again, to justify that ranking, we just look at the enclosed charge. So B is enclosing positive 2Q. Nope, B is enclosing negative 2Q. A is enclosing positive 2Q. And C and D are enclosing positive 3Q. So we're just ranking that. Follows. So if you're actually asked to do this numerically, again, we don't need that much to actually do these Gauss's law problems. Suppose a positive 885 nanocoulomb point charge is placed at the center of a sphere with radius 0.1 meters. Calculate the electric flux through this sphere using Gauss's law and not using Gauss's law. So if you're ever asked for net flux, just ask yourself if you can easily apply Gauss's law first before you try anything. So first of all, Gauss's law says that the net flux through a surface is just the enclosed net charge divided by epsilon naught. And we know each of these things. The enclosed charge is 885 nanocoulombs. And then for epsilon naught, again, that's a formula sheet thing. This is not Coulomb K, so don't use 9 times 10 to the ninth. This is conveniently 8.85 times 10 to the minus 12. And I say conveniently because I picked it so that the numbers divide out. So let's see, if I bump the decimal over here, we should get 100,000 as our number. And then for our units, remember electric flux is E times A. So electric field is measured in newtons per coulomb. And area is meters squared. So that's using Gauss's law. But what if we didn't want to use Gauss's law? This is a case where it's actually easy to do it without Gauss's law. We'll see that in many cases you can't do it easily without, but in this case it is because of the spherical symmetry. So again, we know that this is a point charge, so it's going to generate a field that just points out. So notice, no matter where I am on this sphere, I'm going to generate this field that pierces the sphere's area perfectly. So there's no trig or integration required. So our definition of electric flux is that for uniform E fields, we just multiply the perpendicular component of the electric field times the area. And the electric field for a point charge is kq over r squared. And the area of a sphere is 4 pi r squared. And again, this is very similar to a problem we did in the previous section where we tried to gain some intuition for Gauss's law. Again, it did give us all of these things, but we are going to simplify a bit more because remember that instead of writing this as kq over r squared, remember that Coulomb K is equal to 1 over 4 pi epsilon naught. So I could have instead wrote this field as 1 over 4 pi epsilon naught times q over r squared times my area. And here's where that area of the sphere and the inverse square law dependencies come into play, because we see that this r cancels with this r, and this 4 pi cancels with this 4 pi. So we're actually just left with q over epsilon naught, which we already computed over here. So we get our same field. Not a coincidence at all. So again, that's just some intuition. I could have just plugged in numbers. I could have plugged in 9 times 10 to the ninth times 885 times 10 to the negative ninth divided by 0.1 squared times the sphere area. Could have done that, but I just wanted to show you these are equivalent. Suppose the radius of the enclosing sphere is doubled. Indicate whether the net flux increases, decreases, or stays the same. Well, our first case might have something like this. Our second case, we might have something like this. And if we look at what Gauss's law states, because that's what our first justification should involve, Gauss's law states that the net flux is equal to the enclosed charge divided by epsilon naught. So if the only thing I'm doing is doubling the radius of the enclosing sphere, phi has to stay the same. Because by Gauss's law, if we have the same Q enclosed, that means we have the same flux. Flux through a surface only depends on the enclosed charge. So we can stop there. But again, I really want us to gain some intuition behind this fact. And we've really tried to like get us to kind of understand it as we've gone through, but we're going to just write it in words here. So, how do I say it without referencing Gauss's law? Well, that means that we should probably start from the definition of electric flux. Our electric flux is the piercing E field times the area. And we know that E is proportional to 1 over r squared, and area is proportional to r squared. So what does that mean? Well, that means that that electric flux is going to be proportional to E times A. So this is proportional to 1 over r squared. This is proportional to r squared, which is going to be constant. And this works for the sphere specifically, but again, a similar argument can be constructed for any other shape. But the sphere works really nice for this case. Because again, we know the field falls off via the inverse square law, and the area increases quadratically because of the pi r squared in the area formula, the 4 pi r squared. Now we have a case where Gauss's law is usually our only way out. Suppose I have a point particle that's placed at the center of a cube. And here's where we have to read. Determine the electric flux through the top face of the cube. I don't want the electric flux through the cube. I just want it through this top face. So here's where we have to utilize symmetry for the first of many, many times with Gauss's law. So it's important it's placed at the center of the cube. So what we know for sure, and this is true regardless of where this point charge is that the net flux through the surface is the enclosed charge divided by epsilon naught, which is negative q over epsilon naught. Which makes sense, because I don't care if it's a cube or a sphere, like it's definitely still a sink going on over here. And if we just want the top face, well, it's at the center of the cube. And no matter how I move this cube around, it's symmetric. So this means that by symmetry, the flux through the top face is just going to be 1/6 of the total flux, because each of these 6 faces share the total equally. It doesn't matter how I spin the cube due to that radial symmetry and the fact that the Q is at the center, it's just going to be 1/6 of the total. Because there's 6 faces of a cube. If you had a different shape, of course, it might end up being different. So this is just negative Q over 6 epsilon naught. Although since it's no, we can't put the negative. Should put. Suppose the charge remains inside the cube but is moved closer to the top face. Why is it no longer simple to determine the flux through this face? So again, I've moved this point charge slightly closer. So what we do know is that the net flux, it's still negative Q over epsilon naught. That has not changed. It's the same point charge. But we know that symmetry is broken. So this means that phi top is no longer going to just be 1/6 of the total. Because if I'm closer to this face, I can't say for sure that this is going to take up exactly 1/6 of the flux. It could, because of course there's still that inverse square versus square relationship. Like it could be, but we don't necessarily know what's going to happen before actually working out the fields. So when trying to do flux through specific faces, we have to look for symmetry. If there's no symmetry, we can't. So symmetry being broken is really the main thing. And another result that we can connect with this is when we talked about electrostatics, we said that potential is the same everywhere in a conductor, and E is 0. And this forces all these charges to live on the surface of a conductor. And as a result, you can't enclose any charge if you're inside the surface of a conductor. So what this means is that we can figure out how charges are going to distribute themselves on conductors with multiple surfaces. So if your conductor just has one surface, like a like a hollow sphere, all your charge is going to go on that outer surface. But if you have something with an inside and an outside, it's going to distribute like this. So if you are surrounding a point charge, no matter what, charges in the conductor are going to move to the inner surface to cancel whatever it's looking at. Because if I have any sort of surface that encloses the inside of a conductor, I can't have any E field. And if I can't have any E field, that must mean that I can't have any net enclosed charge. So as a result, we know that you can't enclose any charge, meaning whatever charge is on this surface must be canceling whatever is inside. But you also have to use conservation of charge to this scenario because our shells have some sort of amount of charge they're allotted. They have a net charge and it can't just disappear. So if you've given some of your charge to the inner surface, the outer surface must hold the rest of it. We can use charge conservation to figure out the outer surface has to hold actually the net charge of the system, which is the Q of the shell plus the Q of the inside. We'll show this both ways. And this actually has to work because of the shell theorem, which says that outside any sort of spherically symmetric object, it looks like a point charge that holds the net charge of the system. So if I just see an object with charge big Q that's surrounding an object of charge little q, I know that if I'm outside the whole thing, I must just see a point charge of Q plus Q. And this works based on charge conservation, like we'll prove this shortly. But again, that's how it distributes itself. It's always easiest to figure out what's going on in the inner, because the inner just cancels whatever it's looking at. Because I must have no net charge if I'm inside the actual bulk of the conductor. So this is the case of like we'll have a charge living in a cavity, and we're going to be interested in the surrounding areas. So let's prove it. A conducting shell with charge big Q encloses a net charge little q. Verify each of the following. First, we want to verify the charge on the inner surface must be minus Q. So here we're going to apply Gauss's law. So I'm going to draw myself an enclosing surface here, sort of like this, for my first part. And this enclosing surface, it definitely encloses the cavity, but it also encloses the inner surface, which we're going to call that Q inner. It's going to have some sort of net charge on it. So by Gauss's law says the net flux through any surface is going to be the enclosed charge divided by epsilon naught. And remember that electric flux can also be written as E times area. But E equals 0 in a conductor. So if E equals 0 in a conductor, this means that my net flux is going to be 0. Which means that Q enclosed is equal to 0. And now we can go out and expand this Q enclosed expression after we've shown that this flux actually must be 0. So my Q enclosed, I enclose both the inner shell and the charge in the cavity. So if that must result in 0 net charge, then Q on the inner surface must just cancel the charge it's looking at. So now we can actually do a bit of updating here, where this isn't just Q inner. We actually know it's going to be minus Q. So we actually know that along this surface, spread out is a charge negative Q. It's canceling whatever it's looking at inside the cavity. The charge on the outer surface, therefore, must be the net charge of the system, big Q plus little q. Prove that. So we're actually just going to prove it with charge conservation. So it was defined to us in this problem that the shell has a total charge Q that can be distributed in some way. So we know that if we add up all the places where the charge is on the shell, it must work out to Q. So this just means that Q in the inner surface plus Q on the outer surface must be Q. Because again, there are two places for charges to live on a conductor like this. It could live on the inner surface or the outer surface, because that is the only way to ensure zero E field. Because if there wasn't, charges would be moving inside the conductor. And if they're moving inside the conductor, they have to be moving towards somewhere, so we're not a conductor in equilibrium in that case. So again, E being 0 in a conductor forces these charges to be on the surfaces. We already proved the inner charge was negative Q. So now it's just a matter of adding Q, little q to both sides, and we get Q outer is equal to Q plus little q. We proved this with charge conservation. Another way to do this would be to use the shell theorem. So you could actually prove this part without part A by looking at the shell theorem and saying that outside of the sphere, it should look like the field from a point charge holding the net charge of the system. So I could just shrink the entire system down to that point. And while I would see a negative, I would see a Q at the center, and I would also see a big Q. So I'm seeing this plus this, which is why that lives on the outer surface. So now let's apply this in context to a conductor sandwich here. In the situation below, we have a negative Q that is surrounded by two concentric conducting shells. The inner shell has a net charge 4Q to distribute, and the outer shell has a net charge of negative 10Q to distribute. So these are not the surface charges. This is just the net charge of the shell. So I have 4Q that can be distributed from this one, and I have negative 10Q that can be distributed from this one. What we'd like to do is find all the surface charges. So again, we know that this 4Q is not smeared around the shell. It is explicitly on these two surfaces. So this 4Q is going to split. Some of it goes here, some of it goes here. The negative 10Q is going to split. Some of it goes here, some of it goes here. So we're just figuring out the splitting. So everything's got to add up correctly. So first part of the surface charge theorem stated that the inner surface is always going to cancel what it's looking at to ensure that there's no enclosed charge in a conductor. So the inner shell right here, it's looking at a negative Q, so I have to cancel negative Q. So this is going to be plus Q. You always start by looking at this sort of inner shell. Then there's two methods of figuring out what's going on in this first outer surface. The first one is using charge conservation and saying, well, I have 4Q that I could donate between the two surfaces. I have already given one of the 4Qs to the inner, so the other 3Qs must go to the outer. Method 2 says I could have instead just used the shell theorem and said that outside the system, it looks like a point charge holding the net charge of the system. So I have a point charge with charge negative Q, and I have a shell with charge 4q. So my net charge, which lives on the outer surface, is going to be 4 minus 1, which is plus 3. Same idea for this next part. Doesn't matter how many shells we have, we do it the same way. So inner surface always cancels what it's looking at. So what is this surface looking at? Well, this surface is looking at a charge of plus 3q. And again, we know that because it's the net charge enclosed. Or if we wanted to sum up all the charges it's looking at, we could see we get a 3 plus 1 minus 1. But due to that inner surface canceling, it's always just going to cancel the charge it looks at. So how do I cancel plus 3q? Well, of course, the minus 3q. And then what about the outer surface? Well, I have negative 10 q's to give away, and I've already given negative 3 of them to this inner surface, so that means the remaining negative 7q must go to the outer surface. We could have also proven it with the net charge rule, because again, we have a negative 1, a plus 4, and a negative 10. So if I add up all those, we get, well, negative 1 and 4 makes 3, and 3 and negative 10 makes negative 7. So that gets us our expected result of negative 7q. So here's like a quick like visual of this. So we had like our negative q in the center here. Then we had our first shell, then we had a gap, then we had our next shell. It's suspiciously similar to how I draw my lens diagrams, I guess. So we said that this shell had a net charge of 4q, and this charge had a net of negative 10q. So when we worked it out, we said this canceled, and this was 3. This canceled, and this was negative. So this is how we said our charges were going to distribute in this problem. And again, assume these shells are just wrapping all the way around. That's just how I wanted to visualize it without having to draw the full spheres. So again, our rules is that the inner shell always cancels what it's looking at, and the outer shell holds the net charge of the system up until we can check it all works out, because 1 plus 3 is 4, and negative 7 minus 3 is minus 10. So it works. Yeah, so that's really all there is for Gauss's law without actually finding E fields, which is definitely the more involved topic. But just applying the basics, again, we just have the net flux. And as a consequence, we can determine the charges on any surface of a conductor. And it actually turns out this doesn't depend on conductor shape either. The densities will change along the surface in order to ensure these same rules apply.